All right. Wanted to try something a little bit different to limit any glare coming off of the smartboard. So what I want to talk about today is just more things about roots of polynomial equations, otherwise known as zeros of polynomial functions. And there are a lot of important theorems that we need to be aware of. One of them, as you can see, that we're going to talk about today is the most important, which is the fundamental theorem of algebra. Now, when you look at higher order polynomials, like we talked about finding solutions of quadratic equations and some higher order polynomial equations, but the higher and higher your degrees are, the more and more difficult it is to find those roots and to find those solutions. However, there are a couple of theorems that are going to help us along in making that process a little bit more manageable. First one is called the rational root theorem. Rational root theorem says that if I have a polynomial in standard form, right? It's got a leading coefficient. It's got degree of n. Highest exponent is first. All other terms are ordered from largest exponent to smallest exponent. And we're going to go ahead and assume that each of these coefficients right here, so here, 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 and here, and all along this polynomial, we're going to assume that they're all whole numbers, all integers. Okay. Then, if you set that polynomial function equal to 0, of course, you get a polynomial equation. Then there's a process of which you can find not just whole number roots, but also rational roots. And if you think of the word rational, if you think back to beginning of the year, and I'll go ahead and write this down. If you think back to the beginning of the year, we mentioned that rational numbers are written in the form P over Q, where P and Q are whole numbers. That's what, and so in other words, a rational number being a fraction in any number that can be written as a fraction in simplest form. There are two things that we have to pay attention to with regard to this formula. That's your leading coefficient and your constant term. Okay, those two are going to play an important role in finding any potential roots that a polynomial equation can have. Now, if you have any whole number roots, meaning that if I set that equation equal to 0 and any solution that comes from that is a whole number, then it has to be a factor of my constant term. Okay, so any whole number solutions of that equation must be factors of that constant term. Okay. On the other side of that, if they're not integer roots, if they're not whole number solutions, but they are still rational solutions, any rational solution is going to be in this form right here, plus or minus P over Q, and that's in simplest form, where P is a factor of your constant term, and Q is a factor of your leading coefficient. Okay, so in other words, if we're trying to find potential rational roots of that polynomial equation, then you start by looking at the factors of my any combination of factors of my constant term divided by potential factors of my leading coefficient. And there will be a step-by-step process. We'll tackle how to do this with polynomial equations. Now, moving on. To be clear, the rational root theorem only tells us, it can only tell us potential rational roots of polynomial equations. Meaning that when we go looking for these rational roots using this theorem, not every single not every single number that we find using that theorem is going to be a rational root. In order to find that, well, first we need to determine whether or not that root makes that equation equal to 0 for any of the roots, right? and that may involve some guess and check, okay? And of course, using the rational root theorem may not help us find every root of a polynomial equation, because remember, we've encountered situations where we've had non-real complex solutions along with real solutions. But if we use synthetic division in the right way, it actually can help us break down the polynomial into a much more manageable form so that the equation becomes easier to solve. And in this process, we'll go ahead and explain all of that. So let's say I have a polynomial equation, p of x equals to 0. And I want to find the solutions. I want to find the roots of that equation. First thing that we want to do is use the rational root theorem to find all potential rational roots. So we're going to look for the rational roots first, okay? Then, using guess and check, we'll pick any potential root, substitute it into the equation, and determine if the value of that equation is 0. We're gonna all we need is to find one potential root where the value of the equation is 0 at that point. Okay. Once we do that, we're going to use that number, that root, in synthetic division to factor that polynomial. And sometimes you may need to do it more than once because a root may have a multiplicity of 2 or 3, like we talked about earlier on in this chapter. Okay. Once the remainder is no longer 0, we're going to repeat this process, steps 1, 2, and 3, until when we factor, the polynomial that we're left over with is a quadratic polynomial. And at that point, we can either use factoring or the quadratic formula to find the remaining roots. Okay, now these are a lot of steps, okay, but we're going to go ahead and we're going to use an example to illustrate these steps. All right, so here are two equations. I want to find all the roots of all those equations. Okay, so first things first, I have 2x cubed minus x squared plus 2x plus 5 equals 0. Okay, so I need to identify what's my p and what's my q. All right, let me go ahead and zoom in a little bit so I can give myself some room here. And take this. All right, so p and q. So it looks like this right here is my p. This right here is my q. Well, 5 and 2 are both prime numbers. They don't have a lot of factors, okay? So we want to find every single possible combination of positive and negative fractions of factors of this over factors of this. So remember, for 5, only 2 factors are 1 and 5. For 2, only factors are 1 and 2. So let's suppose that my p is 1. Well, that means that my q could either be 1 or 2. So that's 1 over 1 or 1, and then 1 over 2 or 1/2. And keep in mind, we gotta make sure that for every one of these combinations we find, we're including either plus or minus to that. Now let's say my p is 5. Then once again, my q could either be 1 or 2. So that's either 5 over 1 or just 5, or 5 over 2. And once again, we have to remember plus or minus each time. So these are my potential roots. They're not, obviously there are 8 of them. My degree is 3. So obviously not every single one of these roots could be used, okay? But we still have to try, all right? So here's what I'm going to do. I'm going to erase this, and I'm going to write my roots up here. So that's plus or minus 1/2, plus or minus, oh, actually, you know what? What I'm going to do first is, and I suggest you do this also, start with your whole numbers first. Whole numbers are the easiest to test for if your roots are rational or not, if those are rational roots or not. And of course, plus or minus 1/2, plus or minus 5/2. Okay. All right. So now we're going to do our guess and check here. We're going to take some of these values and substitute them into the equation. Okay. Now, if you're doing this in a calculator, this is where the graphing calculator comes in handy, right? If I go to the y equals section and I type in this equation right here, 2x cubed minus x squared plus 2x plus 5. And I press second and graph, it's going to bring me to a table of x and y values. And I can look through this table and see, and I can see if any of these values up here give me a value of 0 for the polynomial. And if I look at my graphing calculator, when x is -1, y is 0. So -1 is a root for this polynomial. We'll put that off to the side. Now, what do I do next? I go to the, so now that I've found a rational root, I'm going to use that number. And I'm going to use synthetic division with using this number on this polynomial, and I'm going to break it down. I'm going to try to see what its factors are. So obviously, x minus -1 or x plus 1 is a factor. I want to find out what that other factor is. Okay, so -1. My coefficients are 2, -1, 2, and 5. Now, when I do this process, when I get to this point here, there should be a 0 here because this is a solution. It means that x plus 1 is also a factor, right? And then that also means that by the remainder theorem and factor theorems, the remainder here is going to be 0. So let's see, multiply, add, multiply, add, multiply, add. Bingo. So when I factor this, the one factor is x plus 1 or x minus -1. The other factor is going to be x squared minus 3x plus 5. And there you go. But I'm not done yet, because remember, I'm looking for all the roots here. -1 is a root. But now, I know that if this is equal to 0, I know that x could be equal to -1. I need to figure out what kind of solutions I'm going to get from this now. And if I look at 5, only 2 factors are 1 and 5, so I can't factor this using the AC method. I'm going to have to use the quadratic formula, okay? So let's figure out what the discriminant's going to be first. So my A is 1, B is -3, C is 5. Let's see, let me change that real quick. Let's see. -3 squared minus 4 times A times C. That's 9 minus 20, which is -11. So I'm going to have, actually, no, this is plus 20, so that's going to be 29, right? Minus 4 times, yeah, so positive 29. So it looks like I'm going to get 2 distinct real solutions here. So negative b, so that's positive 3, plus or minus the square root of b squared minus 4ac, 9 plus 20, that's 29. 29 is a prime number, so I'm not going to be able to reduce that fraction here. And 2a. So those are my solutions here. Those are my roots. X equals -1. And then if you want to, again, just like before, you can keep it like this, or you can separate it. 3 plus square root of 29 over 2, and then x equals 3 minus square root of 29 over 2. Those are my roots for that problem. Those are my roots there. Okay. All right. Let's try another example. 15x cubed minus 32x squared plus 3x plus 2. Again, same process. Here's my here's my constant term. Here is my constant term. This is my leading coefficient. Okay, 2 is a prime number. Only factors are 2 and 1. 15 has multiple factors. There's 1 and 15 and 3 and 5. So for every one of the factors of 2 as my numerator, I'll have 4 potential different denominators. One where, so if, let's say, for example, P is 1, well then Q could either be 1, 3, 5, or 15. Same thing if P was 2. All right, so let's actually write those out. So it's plus or minus 1 for 1 over 1. Plus or minus, I'm gonna do the ones first here. So 1/3, plus or minus 1/5, plus or minus 1 over 15. And then of course, if my numerator is 2, that's plus or minus 2 over 1. So that's plus or minus 2, plus or minus 2/3, plus or minus 2/5, plus or minus 2/15. So eight, well, technically 16 potential roots, okay? And then just like before, we're gonna start with our whole number ones first, just in case, if you wanna make it, just so to help us make it a little bit easier for us. So my calculator, I'm gonna type in the function, 15x cubed, minus 32x plus 3x plus 2. I'm gonna look at -1, +1, -2, and +2. Let's see. Okay, so it doesn't look like any one of those numbers is our guide. So now comes the tricky part. Now we are actually going to have to look at some of these factors and determine if those values will make this equation equal to 0. All right, so I'll start with 1/3. The plus and the minus. 15, -1/3 to the third power, minus 32 times -1/3 squared, plus 3 times -1/3 plus 2. Okay, that didn't give me 1. Let's try +1/3 instead of -1/3. There we go. So I plugged in +1/3 and I got 0. Okay, so 1/3 is a rational root. Now let's use that number. Let's break it down. Okay, we'll use synthetic division, and I'm going to use a fraction because decimals will probably make it a little bit more messier than need be. All right, so I have 15, I have -32, I have 3, and I have 2. Here's 15, all right? So let's go ahead and multiply. 15 times 1/3, easy enough, that's 5. 32 minus 5, that's 27, -27. Again, easy as pie. The number is also divisible by 3. So -27 times that, that's -9. Add, that's -6. Add, that's -2. Add, 0. Perfect. Perfecto. Okay. So there's my next group of factors, all right? So x minus 1/3 is a factor. Also, 15x squared minus 27x minus 6 is also a factor. And now I just need to use the quadratic formula on that to find my other two roots. And it's very likely that they will be irrational at the least, or they could be complex. Just depends on what the discriminant of the quadratic formula is on that. Let's find out now. Let's use the discriminant now to see what we get, right? So A is 15, B is -27, C is -6. So it's -27 squared minus 4 times 15 times -6. And let's see what we get. So -27 squared minus 4 times 15 times -6. And I get 1089. I get 1089. So let's go ahead and use the quadratic formula on this. Okay. So I know that x is equal to 1/3. Put that up there. X is also equal to the solutions for this quadratic function, which are positive 27 plus or minus the square root of 1089 over 2 times 15. Oops. Wrong color. 1089 is actually a perfect square. Square root of 1089 is 33. All right, so if you want to simplify this before you do the plus and the minus, you can go ahead and do that. It doesn't really matter. I'm just going to go ahead and I'm just going to calculate what this is. So I got 27 plus 33 over 30 and 27 minus 33 over 30. All right, so 27 plus 33, that's 60 divided by 30, which is 2. Okay. And 27 minus 33 divided by 30. That is negative 1/5. Negative 1/5. Excuse me. Now, why did we see 2 as a potential root when we were using the rational root theorem? Well, we probably missed something when we calculated it in. So even if you miss something, quadratic formula, like I said, quadratic formula always works for anything. So I have 3 roots: x equals 1/3, x equals 2, and x equals negative 1/5. And there you go. There are the roots. Okay. Now, if you noticed going back to the last example that we did here, we actually ended up with using the quadratic formula, getting getting a plus or minus in the quadratic formula. It was an imperfect square root, so we ended up with something that looked like something similar to a complex number, right? Well, as it turns out, go ahead and try to zoom out here. Come on. When we solve quadratic equations, right, going back to quadratic equations for a minute, if a solution was a complex number, then its conjugate was also the solution. And then, of course, by the definition of the quadratic formula, if I have an irrational number, an imperfect square root, for example, let's say 2 plus the square root of 3. Well, then that means that 2 minus the square root of 3 is also a solution, right? Now, what does that tell us? Well, it actually leads us to a really important theorem. It actually leads us to a really important theorem here. So if I have a polynomial function p of x is equal to 0, if it has rational coefficients, then if a plus b times the square root of c, right? Like if we did the quadratic formula, we got something like that. If that is an irrational root of that equation, then a minus b square root of c is also an irrational root of the equation. Similar to complex numbers, right? For real coefficients in a polynomial equation, if a plus bi is a complex solution for that equation, then its conjugate, a minus bi, is also a complex root of that equation, right? Here's an example. A quartic polynomial, meaning that, again, quartic, degree is 4. If it has so let's say it has rational coefficients. If the square root of 2 and 1 plus I are the solutions for that equation, what are the other 2 roots of that equation? Well, let's use this theorem, right? Square root of 2, or in other words, 0 plus the square root of 2. And of course, you have 1 plus I, right? If that is a root, then based off of this theorem, this is also a root. 0 minus the square root of 2, or negative square root of 2. Okay? And if 1 plus I is a solution to that equation, then its conjugate, 1 minus I, is also a solution to that equation. Okay? And I can actually go ahead and write out these roots as factors, and I can find out what kind of polynomial this is, right? So it could be, so because these are solutions, I can also write them as factors. X plus square root of 2 times x minus square root of 2 times x plus 1 minus I times x minus 1 minus I, and so on and so forth, right? Which leads us to the next example. What is a third degree polynomial function y equals p of x with rational coefficients such that p of x equals 0 has the roots -4 and 2i? Well, third degree polynomial, and it's 3, right? So I'm trying to find the polynomial that has these two as solutions. Well, -4 is a whole number. So the rational root theorem, the conjugate theorem, doesn't apply to integers. It applies to irrational solutions. Okay, so we're good with -4. But keep in mind, 2i is a solution. That means that -2i is a solution. Now, what's the polynomial function? Well, let's write these out as factors, and then let's go ahead and expand, FOIL everything out, and come up with our equation. Okay, so x minus -4 is a factor, so I'll just write it as x plus 4. X minus 2i is a factor from this, so that means that x plus 2i is also a factor. Now, look at what I got here. If you recall from our section on complex numbers, this right here can be written as the sum of two squares, right? Because it's a complex number and it's conjugate. So let's write it as as the sum of two squares. X plus 4 times x squared plus 2i squared. Well, what's 2i squared? What's 2i times itself? Well, at 2i times 2i, that's actually, hold on a second. I'm writing this wrong. Let's back up for just a minute here, because this will actually show why it's a sum of squares, right? Now, I'm writing this as a difference of squares for this particular reason, because if I write this as a difference of squares, then it's going to actually come out to be a sum of squares anyway, okay? So 2i squared, 2i times itself, that's 4i squared. We know that I squared is always -1, so that's -4, right? So x squared minus -4 is the same as x squared plus 4, and again, that's why it can be written as sum of two squares. All right, so this becomes x plus 4 times x squared plus 4. Now I can go ahead and continue to multiply it out by FOILing. So first, outside, inside, last. So x times x squared, x times 4, 4 times x squared, and then 16. I'm just going to go ahead and put it in standard form just to clean it up. So the third degree polynomial function with these roots is x to the fourth, no, not to the fourth, x cubed plus 4x squared plus 4x plus 16. There's my solution there. Okay. Now, throughout this whole section, we've noticed that the number of solutions, the number of roots that a polynomial equation has, is equal to the degree of the polynomial. What this gives us is it gives us one of the most important theorems in mathematics, and it's called the fundamental theorem of algebra. So, if I have a polynomial of degree n, which is greater than or equal to 1, so it's a polynomial function, it's not a constant function, then the following are equivalent. And then remember, we saw this phrase before, meaning that if one thing is true, all of them are true. Okay? So, the fundamental theorem of algebra says that the polynomial has exactly n number of zeros. So a fourth degree polynomial has exactly 4 zeros. A seventh degree polynomial has exactly 7 zeros, including multiple and complex zeros. We talked about multiplicity, right? We may have to revisit multiplicity here in this section. And because it has the same number of zeros as its degree, it also has that many linear factors, meaning x minus something as a factor, right? And again, that directly comes from what we talked about between roots, solutions, and factors earlier on in the chapter. The polynomial has at least one complex zero. Okay, and that one's pretty broad because you can even if it's only real number solutions, you can write a real number as a complex number. Okay, but that's the fundamental theorem of algebra. All right, so let's do one. We'll do one final example. All right, there are two of them here. I want you to try this one on your own, but for now we're going to finish off with this one right here. We're going to look for all of the zeros of that function, all the roots to the polynomial equation where this is the polynomial. X to the fifth minus x to the fourth minus 3x cubed plus 3x squared minus 4x plus 4. All right, rational root theorem time. My P is 4. There are really only three factors, 1, 2, and 4. But here's the good news. My Q is only 1. My leading coefficient is 1, meaning that any combination of factors of this and factors of my leading coefficient is going to be a whole number because the denominator will always be 1. So I really only have 6 potential rational roots, plus or minus 1, plus or minus 2, plus or minus 4. And that, again, that directly comes from the first part of the rational root theorem. Any whole number solutions of the equation will come from factors of 4. Okay. So for now, let's go ahead. Let's put this in the calculator and see if any of these 6 give us a 0. All right. And when I substitute into the equation, so I have x to the fifth minus x to the fourth plus 3x cubed plus 3x squared minus 4x plus 4. I'm going to press a second and graph. And let's see. -4, -2, -1, 1, 2, and 4. Let's see. Make sure I typed it in correctly. X to the fifth minus x to the fourth plus 3x cubed. Oh, wait, that should be a minus 3x cubed. My bad. Now let's try it. And there we go. All right, so we got quite a few of them, okay? We got quite a few of them. Let's use -2. I'm going to keep the list open because we may have to come back to it. Let's use -2 first, okay? All right, -2. Use synthetic division. 1, -1, sorry. -1, -3, +3, -4, +4. Draw this out. Give yourself enough space. Multiply, add, multiply, add, multiply, add, multiply, add, multiply, add. Okay. So as I'm doing this, I'm continuing to break down this polynomial. Okay. So I've broken this down to x minus 2. No, I'm sorry, x minus -2. So x plus 2 times x to the fourth minus 3x cubed plus 3x squared minus 3x plus 2. All right, I'm going to try again with the same number because -2 might have a multiplicity of 2 or greater. So even when you get a 0 remainder, you want to try that same number again, just in case it shows up more than once as a factor. Okay? Same thing. Break this down. Let's go. Multiply, add, multiply, add, multiply, add. And I don't need to include this, so I'm just not going to include it here. But it doesn't look like I'm going to get a 0 remainder. So Let's go ahead and erase that. We are done with using -2. Come on. I'll just use the eraser here. All right, I'm done with -2. Let's go back to the list. So -2 is a 0, right? It looks like 1 is also a 0. So now we're going to just go ahead and use the number 1. And I'm going to put x minus 1 as a factor and see what else I get. So multiply, add, wait, that should be a 2, not a 3. Multiply, add, multiply, add. And again, once I get here, I'm not going to use this because that's a remainder from the previous one. This is what I want to end on. This is -2, and that is 0. Awesome. So now I have x cubed minus 2x squared plus x minus 2. All right. Here's the trick, though. The more and more you practice these, the more and more you start to recognize what tips I can use to figure this out. Now, the process says to go all the way until this becomes a quadratic function. But look at what I have here. This right here can be factored out using factoring by grouping. Because notice here, if I factor out x squared from this term, and I factor out a 1 here, then I'll have another 0, and I'll have another factored function. So if I tried 1 here, again, let's see what happens when I try 1 here, just in case, right? Let's see, that's multiply, add, and I don't have a remainder of 0. Okay, so I can't use 1. But I want to go ahead and try to factor this using factoring by grouping, right? So off to the side, I factor out x squared here. That's x minus 2. Sorry, not x minus 1. And then minus x minus 2. So both of these have, actually, this should be a plus, not a minus. So both of these have a common factor of x minus 2. So let's factor it out. So x plus 2, x minus 1, x minus 2, because remember, so that's a factor. So all my zeros, so my zeros so far, -2, positive 1, and positive 2. Okay. And this will factor to x squared plus 1. Well, x squared plus 1, if I set that equal to 0 and solve, or if I recognize that this is a sum of squares, okay? So my roots are my zeros. I have -2. I have positive 1. I have positive 2. If I set this equal to 0 and solve, move this over, x squared equals -1. Take the square root of both sides. I and negative I. And look at that. I have 5 zeros. My degree is 5. I'm good to go.